Now that we're able to get our Stepcraft machine to run at 100% on each axis, it's time to test its performance under load. To do so, change your feed rate to 100% and begin by putting 2 fingers of pressure on each axis. We'll test our y-axis. Start by placing your elbow on the machine bed and 2 fingers in the center of the gantry. A wireless mouse or keyboard helps a lot with being able to control your machine and test it yourself. There we go. That took a good amount of pressure to get my y-axis to stall out. Continue further down and try again. Again, a good amount of pressure was placed on the gantry. Lastly, we'll move it up towards the front and try this exercise one more time. That one took a lot. Now, we'll test the travel of the machine in the other direction. Same concept, but this time we'll place our elbow on the machine table and our 2 fingers around the back of the machine. Very strong. I couldn't even stall it out. Again, we'll test in the middle. Almost impossible. And lastly, near the end. Took a lot of force. You can see the machine table actually moved. Now, after you've stalled out the machine, it's going to lose steps, meaning you must home the gantry before going on to moving the machine at all on any of the axes. Otherwise, the axes will collide with the other end of its travel, as it is not in coordination with the value displayed in CNC. I will now home my y-axis and begin testing on my z and my x. Now once y is homed, I like to move it a little further out so that it's a little closer to me. Next, we'll begin by testing our z-axis. Takes a good amount of pressure. The binding occurred far easier and with far less pressure than it did on the y-axis, partially due to the fact that the y-axis is far stronger than the z or x. That being said, the amount of pressure required to stall out my x-axis was a little insufficient for my liking, and this is a good time to note that the x-axis is going to require some final adjustment. We can continue with our x-axis testing. You can hear the noise and pitch changes as I apply pressure and as it gets closer to stalling out. If your machine is moving perfectly at 100%, but you're noticing a sound like that, chances are your machine will stall out and lose steps under load. Lastly, we'll test it at its furthest travel. Again, a very similar amount of pressure was required to stall it out. This is a good sign, as it means the adjustment should be pretty simple, as our binding is consistent and not accentuated in one specific area. Now, I'll try my x-axis in the opposite direction. A little bit stronger. Very strong. Now that we've tested our y-axis, x-axis, and recorded our results for each, it's time to test our final axes, our z. First, we'll test it moving down. Very strong. I actually can't get that to bind using just 2 fingers. Next, we'll test our z-axis moving back up. This is often easier to get to stall out than it is moving down, but still should be quite rigid. That took a good amount of pressure. While it did take some pressure to make this stall out, it didn't take as much as I'd like it to, and thus I'm inclined to think that both x and z need a little bit of final adjustment. Depending on your results after testing each axis, you should have a good idea of what needs final adjustment and what seems nice and rigid. Our end goal is to have all 3 axes very strong and able to keep moving under load. When testing at 100% jog feed, keep in mind that the stepper motors have the least amount of torque when moving the fastest. This means that while an axis might stall out with just 2 fingers of pressure at 100%, it will be able to power through a load similar to the one we applied at 85 or even 90%. We maximize our jog feed to accentuate any issues so that we can fine-tune them and catch them before running our first project. After testing all 3 axes, make sure to home them again, as they have now lost steps and are not located where the software thinks they are. We can do this by homing each one individually or hitting the Home All button.